And I hope everyone enjoyed the poster session or a little bit of a break. I'm excited for this afternoon session, or to kick this off with Daniel Xu, who is an associate professor of computer science in Columbia, where he's also a member of the Data Science Institute. His research is very broadly with many focus areas, most importantly, I think, for the issues of data science, machine learning, theory of computation, and one of his specialties is algorithmic statistics. So today he's going to talk about an approximation power of two-layer networks with random ReLUs. Daniel, thanks for making it. Take it away, and if you have questions along the way, ask him. Probably we have a few minutes for discussion later. You can submit questions anytime in the chat window also. And yeah, sit back, relax, and enjoy.
Okay, thanks for the introduction, and thanks for the invitation to speak here at this workshop. So I'm going to be talking about this joint work with Clayton Sanford, Rocco Servedio, and Vlatakis. Okay, and this is about approximation power of two-layer networks of random ReLUs. So what do I mean by that? So the main object that we're going to study is this family of two-layer ReLU networks where the top level weights are arbitrary, but the bottom level weights are random. Okay, so in other words, it's this linear span of a certain number of random ReLU functions. These ReLUs, I'm sure people are familiar, it's just this piecewise linear function. And so we call these types of networks random ReLU networks. Okay, just to make it more concrete, so this is what we mean by random ReLU networks. It's the span of these kinds of functions, these GI functions. And we're interested in the approximation capabilities of these types of networks as a function of the width of the network, the number of ReLU functions you're linearly combining. And so, kind of question that we may want to answer is, suppose you are interested in approximating, let's say, Lipschitz function, let's say L Lipschitz functions. You can ask then, what's the minimum width, the value R, such that random ReLU networks of width R can approximate any L Lipschitz target function up to some error, let's say an L2 epsilon. Since these networks are random, because the bottom level weights are random, we just asked that this approximation be possible with some good probability, let's say 90% probability for any target function. Okay, and the L2 error that we're going to be concerned with is the mean squared error, where the input is drawn uniformly at random from the cube -1, in d dimensions. Okay. So any questions about the setup, the approximation question? Okay, so we're going to try to give upper and lower bounds on this minimum width quantity. And importantly, we want to do this for all dimension d, all error values epsilon, and all Lipschitz bounds capital L. Okay, so why is this an interesting question to study? Of course, you may care about training neural networks. I'm sure people are interested in this. And usually the network parameters are going to be initialized randomly at the start of training. And so you may want to know, what kinds of functions these networks at the start of, near or, close to the start of training, what can these types of functions approximate, especially if you do not modify the weights too much. Okay. It also turns out we'll be able to say something about kernel methods, because kernel methods, I'm sure people are aware, are very closely related to this class of random networks. Okay, but approximation questions of this form have been studied for a long time. So what was there new to say about this? So really our technical motivation to try to clarify some issue that's a little bit muddled in the literature, namely this interplay between the dimension and this kind of relative error quantity, which the relevant quantity here is this ratio epsilon over L or L over epsilon. And somehow the difficulty to approximate this class of functions, Lipschitz functions, is going to increase both as the dimension gets bigger and as L over epsilon gets bigger. Okay? But exactly how these things trade off is not clear in the literature. And so that's what we were trying to address. Okay, good. So I'm going to give an informal overview of how we answer this basic question. What's the width needed to approximate L Lipschitz functions up to L2 error epsilon? And of course, the answer is going to be that it kind of depends. So if if this ratio L over epsilon is regarded as a constant, then it turns out the answer is just polynomial in the dimension. And if the dimension is treated as a constant, then this is polynomial in L over epsilon. And it's really only exponential in the dimension if this ratio L over epsilon is something that's growing proportional, let's say to at least square root d, okay, or faster, which means that either the functions that we're trying to approximate in higher and higher dimensions just have slopes that are increasing with dimension, or that the error that we care about is also decreasing with the dimension. And so our upper and lower bounds are going to interpolate between these 2 points for all values of d and this ratio L over epsilon. And I'll give more precise bounds later in the talk. Now, of course, this is something that approximation questions of this form have been considered in the literature before, but I said that it's a little bit unclear what the answer should be from if you just read the results in the literature. So there's, in the 90s, there were definitely a lot of lower bounds and upper bounds on the width needed for neural networks to approximate things like Lipschitz functions and other classes of functions, even if the bottom level weights are allowed to be arbitrary, not just random. Okay, but the kind of the catch, including in a lot of these works, including the one that's quoted here by Meyerov in '99. They really only imply some kind of width lower bound that's exponential in dimension asymptotically as L over epsilon goes to infinity. Okay, so they're really thinking about the error they want to be extremely small, and it's possible that this lower bound only applies after L over epsilon is some function of the dimension. Let's say it could be linear in the dimension, exponential, or anything else. It's really not clear at all from the theorem statements or the proofs. Okay, so this is something that's been a concern in recent years, and there's more recent work in the past several years, a couple of years, by Yehuda and Shamir, and then a follow-up paper by Kamat, Montasser, and Schrebro, where they give explicit lower bounds, non-asymptotic lower bounds for this kind of class of random ReLU networks, but only for approximating functions where the Lipschitz constant is something that's actually growing with the dimension, something that's polynomially large in dimension. So this is a bit of a gap in terms of what the right answer is. On the upper bounds, there's a little bit more clarity. So there's a nice paper that kind of uses some techniques from the literature, well understood in the literature by Andoni, Panagrathi, Valiant, and Zhang. And they are concerned with approximating degree K polynomials with things like random ReLU networks, and they show that you can do this with this d to the some constant times the degree K. And if you plug in some results about polynomial approximation about Lipschitz functions, it tells you that if L over epsilon is a constant, then you just need again just polynomial in the dimension width. And then on the other side, if you think of the dimension as being a constant, or L over epsilon as being the main quantity that gets large, you can think about what happens with this even L infinity approximation. And there's work by Bach and then later G, Telgarsky, and Shan that shows that you can approximate Lipschitz functions with width that's exponential in dimension, but polynomial in L over epsilon. Okay. And of course, this L infinity approximation is stronger than L2 approximation, but it turns out that's going to be asymptotically tight as well for as L over epsilon goes to infinity. So, reviewing this kind of this prior work, I know this is just a smattering of some of the prior works, but this is really, I think, the picture that that you get from looking at the literature. It's really not at all clear, what the right answer should be, and doesn't tell you anything about what happens in any intermediate range. Okay, so this is really what we're trying to clarify in our work. Okay, so in the remainder of the talk, I'm going to describe to you our upper and lower bounds on the minimum width, give an idea of the proof proofs. Some of them are pretty standard, but I think there's some interesting aspects to them. And then just describe a few kind of implications of these upper and lower bounds. Okay, so let's get into what the main results are. So this is a quantity that we're going to try to study. This is the smallest with R, such that linear combinations of R random ReLU functions can epsilon approximate any L Lipschitz target function, say F star, with some good probability. We just pick 90% as as our number. And we want to know this quantity for the hardest L Lipschitz target function. Okay. We want to know what this quantity is for every possible F star target function F star. And it turns out that our results will be given in terms of a certain combinatorial quantity, which we just call Q sub KD. And this is the number of integer lattice points in a ball of radius K in d-dimensional Euclidean space. And this quantity is going to show up in both our upper and lower bounds. Okay, so here's the upper bound. The first theorem says that for the minimum width for any L Lipschitz target function, okay, for any epsilon in dimension d, the minimum width is at most some power of Q sub KD for K is something proportional to L over epsilon. Okay, I think that the power is maybe even just 2. And this is achieved with some distribution over the parameters. So these random ReLU functions, you have to pick the parameters of the bottom level weights from some distribution, and the distribution is some simple one where the ReLU functions are drawn IID. Okay. So this quantity QKD for K being roughly L over epsilon gives you an upper bound on what the minimum width requirement is. And we have a matching lower bound that says this is type up to this exponent, the constant in the exponent. So namely, for any parameter distribution, any way of randomly choosing the bottom level weights, there will be some L Lipschitz target function for which the minimum width has to grow at least linearly with QKD, where again K is something proportional to L over epsilon. Okay, and in fact, this lower bound is something that's not even specific to random ReLU networks. Maybe some of you have, if you kind of think about it for a little bit, nothing's really special about random ReLU networks. It just applies to any method of choosing a subspace of dimension R that's independent of the target function. Okay, and so I'll describe what some implications of this later. But the upshot here is that this combinatorial quantity QKD, where K is roughly L over epsilon, is really capturing what tells you the interplay between D and L over epsilon in this problem. Okay, so I should say a little bit more about what QKD is, just to give you a better feel for what it means. So that's the definition again. So it turns out this quantity is something that's been studied as the subject of this problem called the generalized Gauss circle problem. So I guess Gauss looked at this in dimension 2, thinking about circles. He wanted to ask what happens as the radius K gets very large. So what they're doing there, they're trying to approximate the area of the circle or the ball with the area of boxes where the side length of the boxes are 1 around all of these grid points, or at least the grid points containing the ball. Okay? And so as K, the radius gets bigger and bigger, the discrepancy between the area of the ball and the area of these boxes is getting smaller and smaller. And I guess Gauss is very interested in understanding what the behavior of this discrepancy as a function of the radius K. Okay. But so Gauss did it for dimension 2, but you can of course ask what happens for any dimension. And it turns out that the approximation that's shown on the right, is pretty accurate when K gets really large, at least comparable to square root D. Okay, and in that case, the right answer is that QKD is really exponential in the dimension. But on the other hand, the radius is small compared to the dimension. So in other words, if the dimension is, let's say, large compared to K squared, then the behavior is rather different. Okay, and then instead you can use a, I guess, simpler combinatorial approximation to give explicit bounds on this quantity, okay, upper and lower bounds. And then, in this regime, it makes more sense to think of it as something that's exponential only in k squared rather than exponential in the dimension. Okay. And so this is really how we, get those informal answers to the question I posed a few slides ago. So the minimum width you need to approximate Lipschitz functions is polynomial in dimension as long as L over epsilon is a constant. It's polynomial in L over epsilon as long as the dimension is a constant, and exponential in something proportional to d, when L over epsilon really is growing like square root d. Okay, so that's how we get the informal answers from before. Okay, so let me say a little bit about the proofs. The upper bound is actually pretty standard. We kind of follow a recipe that people have been using in recent years to show these types of approximation results. And the one that I think makes it extremely clear is this paper that I quoted before by Angioni et al. In 2014. So it's kind of a two-step process. What do? You use Fourier analysis to try to argue that Lipschitz functions can be approximated by low-degree polynomials. And maybe like the standard way you might do this is to take some orthonormal basis and take the tensor product basis. And here, because of the way we set things up, we can in fact take an orthonormal basis that's basically these sinusoidal ridge functions, like sine applied to some linear function of x and cosines of some linear function of x. And the directions of these linear functions are taken from the integer lattice. Okay, and that might give you a hint as to why this combinatorial quantity comes into our results. And then, okay, and the second step is kind of the standard thing now. Use this kind of infinite width ReLU representation for sinusoidal functions. And this tells you what the parameter distribution should be so that you can basically approximate these basis functions using these random ReLUs, and that's therefore you can also approximate any low degree trigonometric polynomial. Okay, and that's what ends up giving the final bound. The second step is actually really standard because we only have to approximate these ridge functions. Once you only care about approximating ridge functions, things are pretty easy. So really all the technical work goes into the first step. Just say a quick word about the lower bound. The lower bound, I think the argument that we use is really kind of the earliest time I saw it was from Barron in '93. So the gist is this following simple fact. I think it's kind of a nice fact. So it tells you that if you have an orthonormal basis, let's say with n functions in some L2 space or Hilbert space, any subspace of that, any subspace that has dimension much smaller than n, it's going to be pretty far from at least one of these basis functions. And how far is just exactly this quantity, the square root of 1 minus r over n, where r is the dimension of the subspace. Okay, so that's it's like a simple fact, or I guess Barron doesn't write it explicitly like this, but it's just really what he's saying. And maybe this shouldn't be too surprising. It's actually extremely simple proof. But this is sort of enough to match the upper bounds. Okay, and it's really just a matter of choosing the right family or the right kind of family of hard orthonormal functions. Okay, and then of course what we're going to choose is these sinusoidal ridge functions from the upper bound proof, and that tells us that you have exactly q sub kd of these where that are going to be around order k Lipschitz. Okay, and then you just combine these things with some scaling argument that gives you the lower bound. And this argument really has nothing to do with how we choose the approximating subspace, right? As long as the subspace is something that's independent of the target function. Okay. But if you're thinking about these random ReLU networks, specifically about random ReLU networks and the way that people tend to choose the parameter distributions, these parameter distributions are usually kind of invariant and in various ways. And in particular, they'll be invariant to the to coordinate permutations, so they don't treat one coordinate differently from any other one. And in these cases, then basically all of the sinusoidal ridge functions will be hard to approximate, including the one that's shown here. Okay, so that's the lower bound. Really, it's a extremely simple argument, but it's I think it's nice that it's it's an argument that's simple. It tells you something that kind of gives you the type bound. Okay, let me just say a few consequences. I'll probably just say one or two of them. Okay, so there's a lot of
5 minutes, so
yeah, thanks. There's I guess there's a lot of recent interest in this subject called depth separation, where people are interested in understanding what functions can be represented by polynomial size deep networks, but can't be approximated by polynomial size shallow networks, let's say with better than constant error. And so far, all the kind of hard function people have come up with to exhibit this kind of separation have been these really oscillatory functions, okay, like the ones that I kind of depicted here. And this is something that's pointed out a few years ago by Safran, Eldon, and Shamir, and they were wondering, they asked in their paper, can we exhibit this kind of separation between, let's say, polynomial size depth 2 networks and polynomial size depth 3 networks? We can exhibit a separation using a 1 Lipschitz function. Okay. So the Lipschitzness should not be the reason that the function is hard to approximate by depth 2, but can be approximated by depth 3. And I guess the answer, in a certain sense, is no. At least if you're concerned with L2 error, and it's something that's implied by our work. If you think about L over epsilon as being a constant, then polynomial in dimension with depth 2 is sufficient. Okay. And so this, they were really asking about L infinity error, but it really kind of shows you that if you were going to try to exhibit a separation, it has to be because you don't care about just L2 error, you care about L infinity error. Okay, good. I'm actually going to skip this next one and say something about kernel methods, because the lower band is something that actually applies much more broadly beyond random ReLU networks. That was just sort of the initial motivation for studying this. So it applies to any kind of way of choosing your approximation function, your approximator, from a subspace that's fixed independent of the target. Okay, and kernel methods are a prime example of this, because they always choose functions in the span of these kernel evaluation functions defined by the training data. And it's kind of well known that kernel methods have a lot of limitations. And the one I want to describe is one that I learned about from Sebastian Bubeck when he was kind of following or interpreting a result of Alan Shu and Lee. And so it's a lower bound for learning parity functions under the uniform distribution in the Boolean hypercube. And the kind of twist here is that we're going to allow the way of finding the approximation to depend to use some extra power, and the extra power is to be able to query to do these kind of membership queries, or in some non-adaptive sense. So what is a non-adaptive membership query? Basically, you get to pick which x's you want to look at, and then after choosing which x's you get you get the corresponding labels, the yi's, and then you can do whatever you want after that. But if you're a kernel method, you're only going to choose your approximator in the span of these kernel evaluation functions. Okay. And so, why is this interesting? Well, it turns out that membership queries are, even if they're non-adaptive, can let you do quite a lot of amazing things. So one thing they'd let you do is they let you learn parity functions in polynomial time, even if the labels are corrupted by noise. Okay, and this is something that's conjectured not to be, is something that's conjectured to be hard if you don't allow yourself membership queries. Okay. And so, kind of a lower bound for kernel methods, even if you're allowed membership queries, these kind of non-adaptive membership queries kind of immediately follows from our lower bound. You just, kind of choose the hard family of orthonormal functions to be the 2 to the d parity functions. And that's an orthonormal basis for this L2 space. And so what we get as a corollary is that, every kernel method, even if you're allowed these non-adaptive membership queries, you're going to need a sample size that's basically 2 to the d, 2 to the dimension, in order to guarantee mean squared error against any target parity function. This is even true without, if there's no noise in the labels. Yeah, so this is kind of an immediate consequence of our argument. Okay, so that's all I really wanted to say. Just to recap, I think the main kind of technical motivation of this work is to really clarify this interplay between dimension and L over epsilon. And we can give, kind of a nice characterization of this minimum width in terms of this combinatorial quantity. And that, lets us get different types of bounds in different regimes that you might be interested in. And try to say some things also about other questions related to neural nets and kernel methods. There's some more stuff in the paper if you're interested. But that's it. Thanks for your attention.
Well, thank you, Daniel, for this excellent talk. We have a bit of time for questions, which is nice. There are already 2 in the chat window, and I'll try to read Mehmet's question, but he may have to clarify a little bit. So he asks, or he comments that your work is about finding bounds for width for approximation issues, but there is another part about estimation with a loss function. And if you have thoughts about that, and if there is a trade-off between the 2.
Estimating things from data, I guess, with the loss function. Okay. Yeah. So yeah, that's I don't. Yeah, that's definitely a good question. This work does not address that at all, except in this very last part with kernel methods, where it does say something about data. Yeah, I think this is a fascinating question. This, I think, probably Ohad or has some more to say about this. But yeah, I haven't really thought about this.
Okay, so just to clarify for me and maybe for others too, so the issue is then going to a loss function where you have finitely many samples, or?
I think so, yeah. I think they want to know, this is all just a question about approximation, but now you need to actually find this function just from data. How do you exactly do this? Yeah, this work does not say anything about that, really.
Yeah, to maybe push you into another direction with a tough question. So you are not talking about the difficulty of the training problem, right?
That's right, yeah.
So are there any conjectures or like hopes this can be, or give at least, I think it can give useful insights though. I know what in width I would need.
Yeah, so I mean, normally when you train, you don't just modify the top level weights, you also modify the bottom level weights, and that's what this work does not really say anything about.
Yeah, I mean, in random feature models, I think the idea is also to keep those weights constant in random.
Yeah, but I think, yeah, probably I don't really know who turns off the training of the bottom level weights when they run PyTorch. But
I don't think they are too common.
Yeah.
Ohad also left a question in the chat window about the upper bound. So what's the that's a good question. So what is the distribution from which the ReLU weights need to be drawn? Can they be standard Gaussian or anything else? And
yeah,
probably.
Yeah, that's a great question. For our upper bound, we have kind of somewhat of a non-standard distribution, just to make the proof easier. We suspect that drawing them from a standard Gaussian should work as well. But ours is some kind of like I forgot what we called it, some coordinate invariant or permutation invariant distribution. You draw them IAD, so in some sense they are not too exotic, but for our proof, we didn't use just the standard Gaussian.
It seems to be happy with that. and I'm happy to do it. Great. So if there are more questions for Daniel, you can still leave them in the chat window, but let's take an opportunity to thank him one more time for this great talk.
Thanks.
And then move on.